We're now into the last part of the course, and our attention is shifting away from trigonometry and geometry and measurement. However, you don't throw those things in the garbage. You do need to know a little bit of each when we're talking about this last part of the course. The units involve two chapters, which are on forces, and a second chapter, which is on stress. So there may be some people here that have experienced this in a past course, perhaps at the college or at another institution, or even in high school if they did physics. What we're going to do in this chapter is talk briefly, and I mean briefly because there's no way you cover all the stuff in this chapter in a realistic way in a few hours. We're going to talk about forces, and forces are the external inputs that act on a structure. So in this unit, we're talking about the stuff that's happening on the outside of a structure. And then the next unit, which is chapter 9, we're going to talk about what happens on the inside of a structure. So for example, this chapter, you would talk about what are the forces acting on a column or a beam. And then in the next chapter, it's about what's going on inside of that material, inside of that structure. So there's going to be a lot of discussion about motion, moving things, acceleration, and speed or velocity. Yes, we're going to be talking about stress in the next unit, Denny. In this unit, we're going to be talking about moving things. As you know, buildings are not intended to move, at least not in the linear fashion. They do allow for some vibration or motion due to wind or other type of inputs. But the idea is that a building or a structure is supposed to return to its original state after those external inputs are gone. In some examples that we'll see in this unit, things are moving permanently. So that's only to expose you to the nature of forces and motion. So this chapter here is really just kind of like a background on some of the stuff in physics that you should know. The way that we're going to approach the chapter is different than the other chapters. All of the content or theory in the chapter is contained, and if I look over here, it's contained in the first, let's see here, in the first 9 pages. So in your booklet, these booklets are available on Blackboard. The first 9 pages contains all the theory. And then afterward, page 10 and onward, are exercises that cover the entire chapter. Hi, Malik. So what we're going to do in this booklet, and for the next booklet in a similar way, we're going to do exercises and go back and forth in terms of the content. So I'm going to just talk briefly about a few concepts today and see how far we get. There may be the possibility, because of the time that we're losing due to the holiday on Friday, there may be a possibility that I pre-record a 1-hour summary of some of the material, and I might just put it on my YouTube channel for the class, our folder for the class there. And I'll have it on Blackboard as well if you want to find the link there. This is only to make up ground because we do lose 2 hours that would be very valuable to us. So the first question here is, we're discussing forces. So this chapter talks about force, mass, and motion. And the first definition is, what is a force? So for those that have studied physics, and you can definitely remind yourself from that stuff back in the day, but when I was first asked what a force is, I remember it was in a grade 11 physics class many years ago, and the teacher goes, "What's a force?" And I just sat there blabbering away some fancy words and whatever. And then the definition of a force is simply what I've highlighted here, or a very elegant definition would be, a force is any kind of push or pull. So some forces are due to contact. Like if you push on a wall, that is called a contact force because you're touching the wall when you push on it. Or if you have a cable where you pull on the cable, you are contacting the cable. So that is another type of a contact force. There are other forces, though, that are not contact. For example, gravity. Like, if I jump up and down, when I jump up, gravity pulls me down. Gravity is not like a rope. It's not attached to me, but it is a force that is due to two objects that are attracted to each other, but not necessarily touching each other. So can you think of another type of situation where there is a force that is not a contact force? Can you think of another force in nature where it's not a contact force? Surprisingly, Denny, wind is a contact force because it's molecules pushing on other molecules. But it's a good try. It was a good try. This is a tough one. For those that have not studied physics, it's not something that's obvious. Again, Malika, water is a contact. When water pushes or pulls, it's a contact force. So apart from gravity, there are other forces that are fundamental. So Ram, yes, gravity is one of them. Thank you, Denny. That's a very good example. So a very famous set of forces that are not contact forces are electromagnetic forces. So both electric forces and magnetic forces. So obviously we're not studying theoretical physics here, and we're not studying electrostatic forces. Thank you, Yanvi. So anyway, we're going to stick to gravity. Now, gravity, that force of gravity, is called something very common. It's called the weight. See that there? So weight is what is the force of, it's the force of gravity that acts on an object. So that's a very important definition. It might pop up in the notes later, but definitely something that I'd like to just get out of the way immediately. So make sure you know that the weight of an object is the force of gravity that acts on the object. Weight is one of many forces that we see in nature. And one thing that is very mixed up or confused by people that are not experts in physics is the idea of mass and force. So here's a very important table that you need to know for this course, and as well just in general for any type of engineering technology, not just construction. So we have here a very, very important table that you need to be crystal clear about. When I write SI here, does anybody know what SI means in the class? What does SI stand for, or what does it represent? What does SI mean? Anybody know in that chat there? Yeah, thank you, Ram. It's the metric system, okay? So in the metric system, we have a force, which is newtons, and we have mass, which is kilograms. Newtons and kilograms are profoundly different. When you have kilograms or mass, mass is how much matter you have or how much stuff you have. It really relates to how many molecules of that stuff you have. Whereas the force is actually the push or pull that acts on that matter. In the imperial system, there is no distinction between mass and weight or mass and force. Both are pounds. So you might be wondering, why is it so weird? Like if you take a look down here, look at this down here. In this example, in the metric system and in the imperial system, if you have an object that's 200 pounds, then the weight of the object is also 200 pounds. But in the metric system, there is a factor there. It's this factor right here, 9.81. So if you want to go from mass to weight, you need to multiply by 9.81. And that's a constant that we see in physics. I'm going to explain in more detail what the distinction is and where this 9.81 comes from. But there are definitions for mass and weight that you are responsible for on page 3. Obviously, I'm not trying to read this booklet line by line. I'm just trying to point out some key things that as you go on your own, and you are definitely responsible to go through the 9 pages. It's only 9 pages of material. You need to go through these 9 pages of material and look over them again, because these definitions are very fundamental. But mass and weight are profoundly different. Mass is how much matter you have. It's just basically how many molecules you have, whereas weight is a force of gravity. So, question, what is the number? The number is 9.81. And don't worry, Denny, because I'm going to start off with an example right from the exercises at this point. So, I mentioned at the beginning, for those that arrived a little bit late, that the first 9 pages of the booklet, it's just theory and discussion. And then the last, after page 10 and onward, it's all exercises. So what I'm going to be doing is going back and forth between the theory and the exercises. So right away, we can go and do a couple of exercises at the end of the chapter. And here's your first exercise. So the answers, of course, are at the end of the booklet as well. It says here, calculate the weight in newtons of a mass that is 483 kilograms. So let me just mention a few things here to support this discussion. So in the metric system, so how's everybody doing? Is it a busy week for you this week? Is it a chill? Oh boy. Exactly. You multiply by 9.81. Now I just want to mention here for the Earth. So if we're not on the Earth, it's going to be a different answer. So in this case, we have W, the weight, is equal to 483 kilograms times 9.81 newtons of force per kilogram, which, yes, indeed, is about 4738. Now, we're going to go to 3 significant digits. The reason I'm doing 3 sig figs is because it says at the beginning of all the exercises to do 3 sig figs. So we're going to say 4740 newtons. That's part A. To complete the question, the question asks us to write the answer in kilonewtons. So that's easy. You can just say that's 4.740 kilonewtons. Now, if you're wondering, how did I do that conversion? Remember that the conversion for kilo is 1,000. So I'll just write that here. Note. That's right, just move the decimal over. So 1 kilonewton is 1,000 newtons. Thank you, Ram. And thank you, Shalon. So for some reason, my PowerPoint is not allowing me to italicize or unitalicize. I have to manually do it, which kind of sucks. But anyway, are there any questions about this example? So there's my 2 answers. And yes, when you do write your final test at the end of the semester, you will get a question this easy. I'm not trying to baby you. I'm trying to make sure I'm thorough with you. So that 9.81 there, don't throw that in the garbage, okay? That number there is super important. But that's for the Earth. If you're on a different planet or under the gravity influence of a different planetary body, it will be a different number. And if you're wondering, like for example, what would it be on the moon, for example? On the moon, it would be roughly 1/6. So you would divide by 6 approximately. You would approximately divide by 6. That would be the gravitational, this is often called the gravitational field. I can write that here. If you want to sound fancy, that's the fancy word. Yeah, And gravitational field, that value there, that parameter, sorry, that constant, depends on the shape and the mass of the planetary body. Anyway, let's move on to the next question, which is the imperial system. So this one's super easy. So there you have it. In the imperial system, there is no distinction between mass and weight. They have the same numerical value. One thing I don't want to see, and I think would be inefficient, is if I give you a question in pounds and you convert it to kilograms, or vice versa. Although you do get an answer which is correct, you're not doing it the most efficient way. You want to keep it simple here. So if you get a question in the imperial units of pounds, just write the answer in pounds. Some people prefer if you write the F here. If you don't write F here for pounds force, that's what that stands for, you still will be fine in my books. Although in some people do want you to write down the LBF to make that distinction between mass and force. So anyway, how do you feel about that? Are there any questions about what I've done with you so far? Did I start off easy with you? Hopefully. Okay. Got to start off easy, you know? It's the first class of the week. So it's not going to get too bad. This booklet's fairly easy, people. I am confident that most people will find this booklet super easy. At least maybe the last example, the last exercise might be trickier. So it turns out that in many years ago, about 400 years ago, Sir Isaac Newton clarified or kind of consolidated how forces act on bodies and how they move based on those forces. So Newton came up with 3 laws of motion. But one of the most famous laws of Newton's, of the 3, the most famous is this one here. The one that, it's not necessarily the one that you recite the most. Most people, for some strange reason, are familiar with Newton's 3rd law, which we'll get to actually later in this unit. But the idea here is that Newton's 2nd law says that if there is an unbalanced force, I guess I didn't highlight that now. If there's an unbalanced force, an object will accelerate. So that's Newton's 2nd law. And Newton's 2nd law is summarized by this equation here, which says F net equals ma. So I'm going to discuss briefly with you some of the features of this and how it works. So what I'm going to do is just insert a slide here, and we'll discuss a little bit briefly about Newton's 2nd law. That's basically the idea, that if you have an object that is subject to forces that don't balance each other out, then that object will accelerate. Not only accelerate, but accelerate. It will accelerate in that direction of the unbalanced net force. So what does that mean here in terms of math? We get this famous equation, which is F net equals ma. Let's discuss the units and the quantities here. First of all, in this course, we will deal with metric applications. So about mass and weight, that's the only place you're going to see pounds in this chapter. We will revisit pounds of force later on in the next chapter as well, but for other purposes. So what are the units here? So the net force, or F net, will have units of newtons, which we'll call N. The mass, or M, will have units of kilograms, and the acceleration, A, will have units of, and the units are a little bit weird here, meters per second squared. So this is kind of like my express summary for what you need to know for the next sequence of calculations. Actually, if you're familiar and become a lot more literate with this equation and this law, you can do pretty much 1/2 of the exercises that remain in the booklet. So a large portion of the remaining exercises deal with this formula. And what I want to do now for the next whatever we have, about 25 minutes or so, I want to just practice some questions with this formula. Then I'll give you some advice about what to read over on your own. And as I mentioned, I may prepare like a 1-hour pre-recorded summary of some of the easier stuff and some of the more historical discussion from this booklet. So, and I'll have, if I do that, I will post it, of course, on Blackboard and give you the link for it. So, this formula, F net equals ma, you can use it for anything. It could be an elevator with cables. It could be a car that accelerates off the line, like at a racetrack. It could be all kinds of stuff. But in this booklet, to keep it simple, you're going to see a lot of these. See this thing right here? You're going to see carts. Cart. Let me say that. Let me enunciate well for you. So here's a cart. And what you have here is an object that has a 60 kilogram mass, and there are forces acting on it. Now, in the vertical direction, there are forces acting on it, but they cancel each other out. So we're not going to talk about the forces in the vertical direction. However, this 150 Newton force that acts to the right is not balanced. In other words, there's not a force on the other side that will neutralize it. So this object is subject to an unbalanced system of forces, and therefore it's going to accelerate somehow. Which way do you think this object will accelerate? Do you think it'll accelerate to the left or to the right? Of course. And I know you said the word move, Shalon, but I'm going to use the word accelerate. Make sure you use the word accelerate. It's going to accelerate to the right. And what will that acceleration be? Well, my friends, it's super easy because the formula is F equals ma right there. See? Let me highlight it. I'll highlight the formula here. F equals ma. You can rearrange the formula, very cute. There it is. And you've seen formulas that are way worse with me, especially on your assignments. I've had you do some pretty nasty formula conversions. But anyway, in this case, if we take the net force and divide by the mass, so if we take 150 and divide by 60, you get 2.5. And there it is, see? 2.5 meters per second squared, and it's moving to the right. So it's what Shalon said in terms of the direction, but also I wanted to hear the acceleration, which is the meters per second squared. In this example, very elegantly, it shows that the units are the nicest possible setup. So that's what you have over here. In that example, we had newtons, kilograms, and we ended up with that. So as long as you stick to these units, which are like the most orthodox type of units that you could have, then everything's going to be smooth sailing. So what we're going to do now is 2 or 3 examples of that type, and then we'll definitely be able to answer a lot more questions. And I think that you'll become very proficient at using Newton's second law for just some basic applications. Let's take a look at some exercises at the end of the chapter. On your own, though, you can try example 3 later, just when we finish class if you have time. You should definitely read over example 3. I'm not saying example 3 is particularly hard. What is the formula if you have A and F net? Oh, just rearrange it, Denny. We're going to practice that right now. So Denny's question is saying, what do you do if it's all scrambled? So I'm going to do that with you with the next examples. So we're going to do questions 3 and 4. Yeah, just change it around to suit the situation. So here's example 3. I promise you, everybody, I know that, I say things are easy, and sometimes, maybe it's not easy for everybody, but generally speaking, my experience has been that students find this easy. So, and don't worry, on your final test, it's going to be carts. It's not going to be like a rocket ship or something crazy. It'll be something very similar to the notes. So here's an example. It says, find the numerical value of acceleration and what is the direction. So Malik, I think you will be pleasantly surprised. So the net force is equal to the mass times the acceleration. This won't answer Denny's question. Denny wanted a question where you want to find the mass. But let's do this question and do question 4, and then maybe I think question 5 has the one with the mass. So Denny's question is exercise 5. But anyway, in any case, questions 3, 4, and 5 represent the 3 possibilities, okay? So these next 3 questions, let's get them done, and then you have all 3 possibilities in your repertoire. So in this case, can someone tell the class what is the net force? What would be the net force? So remember, net is like, in mathematics, means like a difference. So what is the net force here? Well, it's weird, right? Because you got a force over here, and you got a force over here. So my question to you is, what do you do with these numbers? How do you deal with them? Do you add them together? What do you think? Should we add them together? What do you think? Yeah, you got to subtract them. Yeah, it's the difference. That's right, the difference. So I want you to think about like this, okay? What I'm going to write over here is very childish, but I don't care. Okay, you're going to ask yourself which force, and again, excuse my my childish way of saying it. Which force wins and by how much? Does that make sense? If you ask yourself that question, then this question is done. Okay? So clearly the 290 wins. So 290 minus 115. So the 290 wins by how much? What's the difference there? What's the difference there, people? Did you get 175? Okay. And then over here is the mass, so that's 38.2 kilograms. And then A, which is your acceleration. So, I'm going to get rid of the units here because they're a little bit cluttered. So how do you solve for A? What does A equal? Or what calculation do you do? What's the final answer? What's the final answer, people? That's correct. Very good. So how did you get that? Thank you, Denny. Yeah, you got to divide. So if you divide those two things, those two quantities, sorry, you get 4.58 meters per second squared. 3 significant digits. Why don't we find the force of the object? Okay, so Zifeng's question is, why don't we find the force of gravity of the object? So let's talk about that briefly here. So Zifeng brings up a very important point that I kind of dismissed earlier, which is this. There is a force acting down. So in the chat, Zifeng has calculated that force to be whatever it is, 375. But the ground is pushing up. So this guy here, this force here, equals this force here. So those two purple forces, geez, I can't see things today. Those purple forces neutralize each other. So that's why we don't consider them in the discussion. Does that answer your question? Perfect. So it won't matter. But again, I'm not training you to be physicists today. I'm just trying to, brush up on some skills and just introduce you to some of the basics. So we're going to repeat this question now, but this idea for another question. And if you don't mind, I'm just going to move along to the next. Here we go. We have an object here where we want to find a single force. So there's only one force acting this time. And that force is equal to F. So we have F equals. So this is probably the easiest situation. But we have a little bit of a hiccup here. The acceleration is 5.65 meters per second squared. That's okay. But what's up with the mass? What's wrong with the mass? What do we have to do to the mass? Yeah, convert it to kilograms. So the mass is going to equal 14,800 grams, which you should know how to do. You divide by 1,000. That is some basic conversion. And now look at those units. Those units are the most orthodox of units for what we need. So we just multiply that out, and we will have an answer, which will be in newtons. So what's that answer? What's the answer number 4? Anybody? Yep. Awesome. So there you have it, my friends. We have gone through the 2 cases, but don't worry, I didn't forget about you, Denny, because you wanted to see what you do when you want to solve for the mass. So let's solve for the mass. I'll just give everybody 20 seconds to document this question. Of course, I'll post this booklet on Blackboard, and there will be revisions made to it, and I'll post those revisions and update the document as we go through the material. Anyway, so enough of me yapping away here. Here's Denny's question. What is the mass? So you're more than welcome to rearrange the formula. Let's rearrange the formula this time. What would the formula be then? It would be m equals what? What's the formula? Anybody? Thank you, Ram. I'll just work sideways here because it's a little bit cheaper on the screen, maybe easier on your eyes to see it sideways. I mean, I'm not that picky. Like, I like one line of writing per formula, but it's all good. It's all good. As long as you get the right answer, I'm not going to cry about it. Okay, when someone's ready, can they give me an answer there? Any answers? Yep, lots of ones there. Now, it is 1511.11, but if you don't mind, I'm going to put 1510 kilograms because the question says at the beginning of the booklet 3 significant digits. If you're wondering why it's not 1511, it's because I'm using 3 sig figs. Wow. Who's finding these questions pretty easy? These CART questions? Anybody else? Yeah. Look, no games, people. This is not meant to be like some intense theoretical physics exercise. I just want you to be familiar with Newton's second law, which is saying that if there are unbalanced forces, an object will accelerate. And there is a lot of common sense, but the one thing that is definitely not common sense is the definition of a Newton. So that is a definition. So I'm going to put down the definition of a Newton right now. I'll put it right here. It's in the booklet somewhere, but I'm just going to mention the definition of what a Newton is, okay? That's the definition of a Newton. Put that in red. So might as well take that opportunity to just get that out there for you. So without too much effort, we've achieved some good practice on Newton's second law. Yeah, it could remind me of that too. Meters per second squared, yes. Yes. For those of you that are wondering, what does meters per second squared mean? I'm going to get into that discussion next time. So, or I might get into discussion with a short lesson or a short video discussing those historical features and where this comes from. So let me take care of that and decide what to do with that. My priority has been, as you know, for the past 4 days, to take care of tests and grading. So anyway, your homework is question 6. So I'm just going to drop it over here. Homework, okay? And also question 7 and 8, homework. Now, you can definitely go through and do more stuff. Once we finish the lesson today, what I'll do is I will immediately put the solutions right in these spaces here for my solution files. And so that way when I upload this to Blackboard later, you'll have the solutions right at your request. But as you know, if you go to the end of the book, when you go to the end of the book, all the answers are right there. See that? This is a scan of our notes. In addition, this document that I'm giving you on Blackboard, the solutions, I also provide a 2-page summary. This document here is not, I don't think it's in the main course notes. These are my personal notes where I just kind of summarize what are the big things you need to know. See? So see, chapters 8 and 9 summary. This is the chapter 8 part. The chapter 9 part, I'm going to append to that chapter. So this is like my cheat sheet. So if I was writing a test, this is my cheat sheet. And you have my permission to use my cheat sheet. So here it is. Definition of a force, mass and force, some conversions. So we're very familiar with kilograms to newtons now and how you convert. But here's some other ones that you're responsible to know. So I'm not going to give like a long lesson about these ones. These are kilograms to pounds, tons to pounds, kip to pounds, and metric tons to kilograms. There's also some discussion about speed and acceleration, which I will discuss maybe, like I said, in a pre-recorded video. A kip is 1,000 pounds. Kip is 1,000 pounds. And then in the next page is some of the stuff that we've talked about, including Newton's second law and a discussion about mass and weight. So these last 2 pages, I will post this document right when we finish class. I'll convert it to PDF and put it on Blackboard. But I think that's enough for the material today. I think that's a good start. I might have gone a little bit quick in the beginning. I guess I'm trying to make up ground for the time that we're going to lose on Friday. But anyway, as you know, we do not have class on Friday. So I'm going to wish you a lovely week, and I'll stick around for questions. And we'll talk next Tuesday.